All right, so in this section, we're going to start using the information that we learned from section 4.3, which is the basic properties of quadratics, to compute some word problems or to work through some word problems that cover quadratics. Okay, so to start off, we're going to talk about a couple of different models. So the first model we're going to talk about is called the revenue model. Okay, the revenue model in dollars is defined as the amount of money received from a sale of an item that can be represented by the equation below. So this is the equation we're going to be using for these revenue models, where P is the price, is the selling price. Okay, so P is the selling price, and X is the number of units sold at this price. Okay, and R is, again, the revenue. An equation that relates X to P, so remember that an equation that relates just means that you're saying X is equal to something with a P value in it, so it's a relationship between X and P, is called the demand equation. And again, we're going to talk about that here in a little bit. All right, so let's do an example. It says that we have an equation. Let me reduce this. Okay, so it says the marketing department at TI has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators sold is given by the demand equation below. So we're going to be using this demand equation. Remember, demand equation just relates X to P. We want to find a model that expresses the revenue R as a function of the price P. So that's part A. Then we're going to figure out what the domain is of R. Then we're going to figure out what unit price should be used to maximize the revenue, then what the maximized revenue is, and then how many units are sold at the price, and then we're going to graph the function. All right, so let's go ahead and start off by representing or finding the model, so part A. So finding the model that expresses the revenue as a function of its price. So remember that revenue as a function of its price, so this is what we're looking for. So R of P is equal to, and we have this revenue function here, right up here where we started, okay? So we have that the revenue of P is equal to X times P, okay? Now we want our revenue to be a function of its price, right? So P should be the only variable that we have on the right-hand side of this equation. So we need to adjust something. Notice that the X is the thing that's causing us the issue right now, okay? So we need to find something that we have that relates X in terms of P, and we do. It's right here, right? So we have X equals this function or this equation. So that's what I'm going to do. I'm going to replace my X with 21,000 minus 150p. So 21,000 minus 150p. And I have times P. Now, remember to make sure you're putting these parentheses because those are extremely necessary whenever we're coming back to it, because we are going to have to distribute this P into the parentheses here. Okay, so let's go ahead and do that. So we have 21,000 P minus 150 P squared. Okay, so this is our revenue function as it relates to P. Okay, now we're going to take a look at this and we're going to say, okay, well, what is the domain of our function? Okay, on our prices, we want to make sure that our revenue is positive, and we want to also make sure that our prices are positive. So when we're looking at the graph of this, we're going to be focused entirely in the first quadrant. Okay, so where this is the revenue and this is the price P. Okay, so our graph should be something like this. Okay, one way that we can find our our domain is by simply finding the x-intercepts. Okay, and we can do that by saying, okay, this is equal to, so 0 is equal to the function that we came up with, so 21,000p minus 150p squared. We can factor this, right? So we can pull out a p sorry guys, we can pull out 150p. Oh, yeah, 150p. And we will be left with 140 minus p. Okay, so this is how we could factor this. And then remember that we can set a price of, so if we were looking at this first one, right, so p would be 0. So again, we're just looking at where each of these are 0, so p could be 0. Okay, and then if we look at the second one and solve for p, we get that p will be, the other intercept would p would be 140. Okay, so our intercepts would be 0 and 140. Okay, which means that the domain of our function, because we want our revenue to be positive, right? Because if we were to continue graphing these, our revenue would be negative from here on down, so we don't want to deal with those. Same with our price. We don't want our price to absolutely be negative, so we don't want to do that one. So we can set our domain between these two intervals. So we're going to say it can go anywhere from 0 all the way to 140. Okay, so that's our domain. That'll keep us in the positive. All right. Part C is asking us to find the, sorry, let's go back up. Part C is asking what the unit price should be that maximizes the revenue. So remember, anytime we're looking at maximums or minimums, we're looking for the vertex. So we're going to solve for h and k. Okay, in this case, our h is actually going to be the price that we set, and the k is going to be the revenue that we come up with. Okay, so when we're solving for h, we're actually solving for p. So h is equal to p, which is equal to, remember it's negative b over 2a, which we can plug in our information as, let's see, this would be our a, this would be our b. Okay, so we have negative 21,000 divided by 2 times negative 150. Okay, and we get a price to set as $70. Okay. All right, so we have our price that we need to set. Now we need to look at the revenue that we can expect from this. Okay, so to find the revenue, remember revenue is your k value. To find your k value, you simply, let's go ahead and do that. So your revenue is, this is your k value. Okay, so to find your k value, simply plug in the price that we found in for p. And when you do this, like, I'm not going to work this one out with you, but you get a revenue of $735,000 if you set a price for the TI calculators at $70. Okay, and so this is what we're looking at, so that we can expect a revenue set at this price of about $750,000. Okay. Next, it's asking for the number of units that we can expect to sell. Okay, and this is going to be the one that might be a little bit more difficult. So how many units are sold at this price? So now we need to figure out how we can relate this information back into number of units. Okay, so if we look at our original equation, our original function right here, notice that there's nowhere where we have a unit value. Remember, our unit value, the number is the number of calculators, which is x. Okay, none of this relates it to x. So what we're going to do is instead, we're going to use our demand equation. Okay, so we're going to use this right here. Okay, and the way we're going to do this is by saying simply we have x equals, x is being the unit price, or the number of units, x equals, it's 21,000 minus 150 times the price that we set this at, so times 70. Again, I'm going to let you guys do the calculations here, but you should expect to sell about 10,500 units. Okay, so we have about 10,500 units. So again, just to kind of cover back over what we just came up with, we need to set a price at $70 to maximize our revenue. The revenue that we can expect is $735, and then the number of units that we can expect to sell or to need to produce is about 10,500 units. All right, the last thing it's going to ask us to do is to graph R. Now, we have come up with several different parts of this. So we've already actually, I'm going to call this part F up here, where we've started graphing this. Okay, notice that we've already come up with our domain. Our domain is from 0 all the way up to 140. Okay, and then all we need to do from here is simply fill in what our H and K are. Okay, so our H is 70, and our K is $735,000. Okay, that's all you got to do. All right, so let's take a look at this next example. All right, so in this next example, it says a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that enclose the most area? Okay, so we're looking at a couple of different things. So the first thing I would suggest doing is drawing a picture. Okay, so we're going to draw a picture. I don't think I can, yeah. We're going to draw a picture of a rectangle, right, because he has a rectangular field. It says that the farmer has 2,000 yards of fence. So in other words, to go all the way around, he has to use all 2,000 yards of his fence. Okay. Another way to say this is that the perimeter of the fence has to be 2,000 yards. So a perimeter is 2,000 yards. Okay. Now what we're looking at here is we're looking at the area. That's our goal, is we want to find the area. So let's go ahead and write the equation for the area up here. So area of a rectangle is simply going to be the length times the width. Now we don't know what the length or the width of this rectangle is, so we're going to leave this as, I guess I can't move it. We're going to leave this as just we'll call this the length, and we'll call this one the width. All right. So now we need to be able to relate these. Okay. So first of all, the only information that we have is that the perimeter of our rectangle is going to be 2,000 yards. Okay. So what we can do is we can set this equal to the perimeter equation. Remember, the perimeter equation is just twice the length plus twice the width. So I'm going to do that. So 2,000 is equal to twice the length plus twice the width. Okay. And what we need here is we need to relate our function so that it is just in terms of either length or in width. Okay, so we're going to need to get rid of one of those. Okay, so I'm going to go ahead and choose. I'm going to say we're going to build a function so that it relates everything to width. So when we do this, we're going to need to get rid of our length. Okay, that tells us that in this equation here, we need to solve for the length so that we can get rid of it, so that we have something to substitute for. Okay, I'm going to allow you guys to work this out, but I'm going to give you the solution here. Is the length is equal to 1,000 minus the width. Okay, so the length is equal to 1,000 minus the width. Okay, and we can simply substitute that in for the length up here so that we have everything in terms of width. Now then, we're going to take this information and we're going to see if we can come up with a quadratic. Okay, so first of all, let's go ahead and simplify this. This would be A of W is equal to, this would be 1,000 times the width minus the width squared. So if we were to draw this out, okay, you don't have to do this, but if we were to draw this out, you would have a parabola that opens downward that looks something like this. Okay, now we're going to look at those key words, the most area, right? So remember, when we're talking about the most or the least, we're talking about the vertex. Okay, we're talking about the vertex of our parabola. Okay, so HK. Okay, so that's what we're going to solve for. And what we need to think about is what H is and what K is. So let's go ahead and take a look at this equation. So, or this graph over here. If I'm talking about this graph in terms of A of W, W is going to be our x-axis and A is going to be our y-axis. Okay, so when we're solving, it's going to be W comma A. Okay, that's actually what we're solving for when we're solving for the vertex. Okay, and we're looking for the dimensions, which means that we're just wanting the width of this. So let's go ahead and do that. All right, so H is equal to the width. Okay, so H represents the width, which is equal to negative B, which is 1,000, divided by 2 times A, which is just negative 1. Okay, simplify that. I believe we get 500. Okay, so we have a width equal to 500, and remember to put your label. So this would be a width of 500 yards. Okay, so we know now that the width of this rectangle is 500 yards. Okay, so this takes up a total of 10,000 or 1,000 total yards, which means that in order to enclose the most area, the length would also be 500 yards. Okay, and we can find this by simply plugging it into our perimeter, right? So we can say 2,000 is equal to 2 times L plus 2 times 500. Okay, and this will solve for our length. And when you do that, you get a length of 500 yards as well. So the shape that maximizes the area of our rectangle actually turns out to be a square. Okay, and so our answers are going to be the width has to be 500 and the length of our rectangle has to be 500. Okay. If I were to ask you what is the maximized area, all we would need to do is plug it into this function here. All right, so moving on. Well, let's take a look at this next example. All of this worksheet, all of these notes are just going to be examples. Okay, so it says a projectile is fired from a cliff about 500 feet above the water at an inclination of 45 degrees to the horizontal with a muzzle velocity of 400 feet per second. In physics, it is established that the height of the projectile above the water can be modeled by this equation down here. And this is really where we need to start looking, okay? Where x is the horizontal distance of the projectile from the base of the cliff. Okay, so let's go ahead and break this down. So h represents the height of the ball, and x represents the horizontal distance. All right. So it says, find the maximum height of the projectile. Okay, and we can do this fairly simply by simply knowing what the vertex is, right? So remember, anytime we're talking maximum or minimum, we're talking about the vertex of our parabolas. Okay, so we need to know what h and k are represented by, right? So in this case, our y-axis is actually going to be the height of the ball. And our x-axis is still going to just be the horizontal distance, or the x. Okay, so let's go ahead and write that this is going to be x comma h. I'm going to go ahead and make this a capital H so that we can tell the difference between the two. All right, so we want to find the maximum height. So our goal is to solve for this here. Okay, but in order to do that, we need to first start with finding what x is. Okay, and we can do that by solving for h. So h is equal to x, which is negative b over 2a. Okay, this is one of those things that you're definitely going to want to put into your calculator here. Okay, when you do, you'll have something in your calculator that looks like this. It's going to be negative 1 over 2 times. It's going to be 32 over 400 squared. When you calculate this, or when you hit enter, you should end up with a distance of 2,500 is going to be the distance away where it actually hits the maximum height. Okay, so this is part A. Okay, so this is the distance where it hits the maximum height. Now we need to figure out what K is, which is actually going to be the height of the projectile, which we simply plug in 2,500 into our calculator. And when you do this, and again, this is one of those things I'm just going to leave up to you all, you get 1,750 feet. Okay, so the maximum height of our ball, of our projectile, is 1,750 feet off the ground. Okay, so then in part B, it's asking how far from the base of the cliff will the projectile strike the water? Okay, so how far from the base of the cliff will the projectile strike the water? Well, in order to do this, we're actually going to find the x-intercepts. So this is an intercept. Okay, there's a really simple way to do that, and I showed you guys this in class, and we've worked with this quite a bit, but we're simply going to use the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, you're going to type this into your calculator. Okay, so in this case, it's going to be negative 1 plus or minus the square root of 1 squared, which is just 1, minus 4 times a, which is negative 32 over 400 squared, times c, which is 500, all over 2 times a, which is again negative 32 over 400 squared. When you do this, you should get two values. Okay, your two values are going to be negative 458.04, or you'll have 5,458.04. Again, you need to keep in mind what these represent. These represent the distances from our starting point. So if we're looking at our graph, we're shooting our projectile over here, and we're shooting it forward. Okay, so this is going to be a positive value. Okay, so if we're looking at these two choices that we have, we're going to pick the one that is positive. Okay, the other one, so this negative 458.04 is going to be, if we were to continue this line backwards, it would hit at negative 458.04. So that's just saying if we were to shoot the cannon and it shot behind us, that's where it would hit. Okay, so again, these are two answers. This one is where it hits the water, so feet. This is the maximum height of our projectile, and where it hits the maximum height of a projectile. All right. One last example, and then we're going to be done with this section. Okay, and we should be good to go on the remainder of this, the worksheet. It says the Golden Gate Bridge is a suspension bridge that spans to San Francisco Bay. Its 746-foot tall towers are 4,200 feet apart. The bridge is suspended by two huge cables more than 3 feet in diameter. The 90-foot roadway is 220 feet above the water. The cables are parabolic in shape and touch the road surface at the center of the bridge. Find the height of the cable above the road at the distance of 1,000 feet from the center. Okay, so I gave you guys kind of an illustration. Now, this isn't a perfect illustration. Notice that in the description it said that the huge cables actually touch the road surface. So it's right here. So the cables actually touch the road surface in the middle. So if you need to, feel free to represent that it actually touches the road surface in the middle, and we can go from there. Okay, so what I want to do first is I want to use this picture to kind of illustrate our graph. Okay, so I'm going to use the center here as my y-axis. So I'm going to draw a line that goes through my center at the y-axis. Okay, I'm going to call this y. And then I'm going to use the roadway as my x-axis. So I'm going to use this as my x. Okay, and we can actually come up with the equation of this parabola by picking out the parts of the parabola. Okay, so let's go ahead and start kind of breaking this down into what we were given. We are only looking at this from the front, so we're not worried about the length of the roadway or the width of the cables or anything like that. But we do need the information from the front. So it says that the towers, so in this first part, it says that the towers are 746 feet tall. Okay, so we know that from top to bottom, that the towers are 746 feet. Okay, the next thing you'll see is that the towers are also, so from here to here, these towers are also 4,200 feet. Okay, the bridge is suspended by two cables, blah, blah, blah. The 90-foot wide roadway is 220 feet above the water. Okay, so this is another part that we're going to need. It says that the roadway is 220 feet above the water. Okay, so what I want to do is, because we're using the roadway as our x-axis, in other words, that's where y is equal to 0, I'm going to go ahead and call this, I'm going to use a different color here. I'm going to call this our origin. Okay, so we're going to call this the point 0, 0. In other words, the length of the cables are 0, and it's equidistant between the two towers. Okay, so the next thing we need to do is kind of talk about what it means to be a parabolic in shape. Okay, so this is where the math is going to come in. So the math. All right, so this is parabolic in shape, so we know that our function will end up maybe looking something like this. Okay. That being said, we're given the vertex. We know what the vertex is. We just need, so why don't we change this so that instead of that, we have vertex form. Okay, so again, in class, we figured out that vertex form is the same as quadratic form. Okay, so those are the same thing. So we're going to use this information to come up with the equation so that we can actually figure out what the question is asking. Okay, so let's go ahead and do this. All right, so we know what our vertex is. Our vertex is 0, 0. So we're going to say f of x is equal to a times x minus 0 squared plus 0. All right, well, this would mean that we just have f of x is equal to a times x squared. Okay, now here's the issue. We don't know what a is right now. Okay, so in all of these we have a, but it is simplified from what we have here. Okay, so what we need to do from here is figure out what a is. And the way we're going to do that is by figuring out what one other point is on our parabola over here. Okay, so we're going to need to figure out what one other point is on our parabola. The easiest point to do that is at the top of our towers. Okay, and the reason that's the easiest to deal with is that we're given all of the information there, right? So we know that the distance from the center of the bridge to the tower, right? We know what that distance is. Okay, the distance is going to be half the distance from one tower to the other, right? So it's going to be half the distance from one tower to the other, which is 2,100 feet. Okay, then we can figure out what the height of the tower is above the roadway, which again, remember our roadway represents our x-axis. Okay, and the way we can do this, we've got the total height of our tower, and we can subtract the height, the distance from the water to the top of the roadway, and we can get that the distance is about 526 feet, or the height of the roadway is 526 feet. So we know that this point would be 2,100, comma 526. So we've got our x and our y. Okay, so we can actually plug those values in. So we have 526, okay, that's our y value, is equal to a times 2,100 squared. Okay, I'm not going to have you guys worry about actually squaring these unless you want the decimal, but in this case, I'm just going to simply divide by 2,100 squared from both sides, and we have our a. So a is equal to 526 divided by 2,100. Okay, so our function, the function that we can use, I'm going to write it over here. So function is going to be f of x is equal to, we've simplified it as far as it'll go, down to 526 over 2,100 squared x squared. Okay, so we have our function. Now all we've got to do is figure out what they're asking for. So it says find the height, so this is the green part here. It says find the height of the cable above the road at a distance of 1,000 feet from the center. Okay, so in this case, remember that the height is we're representing using f, and the distance is going to be, or the distance from the center is going to be x. Okay, so we know, so we're calculating f of 1,000 because 1,000 is the distance from the center. That's 526 over 2,100 squared times 1,000 squared. Okay, give you guys a second to calculate this. But when you do, the height of the cable is about 119 feet. Okay, and that's it. Okay, and in class we'll talk about interpretation. I do want you to be able to interpret this. I'll kind of give it to you in words, but I'm not going to write it down. Okay, so if I were to interpret this, I would say at 1,000 feet from the center of the bridge, the length of the cable you can expect it to be about 119